Let us get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Hold on, my phone is connected to my headphones here. Let me disconnect that because I keep hearing notifications. Okay, so we're good. Hopefully you had a good week. Hopefully you watched all the lectures. Like I said, technically at this point, you're only supposed to get up to lecture 11. However, gave you guys some extra time. Hopefully you got up to around lecture 14 because your quiz next week will cover up to lecture 14. So for today, what I want to do is just take some questions on lectures 9 through 14, which is what your quiz next week will cover. That being said, let me start to share the screen here so that we can actually get on with things. So hopefully you're seeing the screen now. Okay, so let me make sure that I can also see the chat window here. Okay, so quiz next week. Covers lectures 9 through 14. So what are the things you'd need to be able to do on that quiz? So you should know about the second derivative. You should know about the idea of concavity and inflections. You should know about the first derivative test and the concavity test. You should also know about derivative rules and formulas. So that's basically, you should know how to find the derivatives of some basic functions, for example, like polynomials. You should also know how to find the derivative of an exponential, derivative of a logarithm, that sort of thing. So about the basic functions, you should know how to find their derivatives. So derivative rules and formulas. So something that tells you how to find the derivative of a specific type of function, I call that a formula. The rules refer to things like the power rule, the product rule, the quotient rule, the chain rule, all those, general rules. What else? I think we cover implicit differentiation. So that's basically, you want to differentiate an expression that includes your dependent variable. So there's some inside function. I still have people trickling in here. There's some inside function here that you don't know for sure what it is. And so you want to differentiate implicitly. Is there anything else? I feel like there was something else. No, I think that covers it. So that being said, any questions on this topic? So hopefully you came here and you got with someone sending me a private message here. That's okay. So hopefully you got through all these lectures, so you'll know questions that you might want to ask me. And so at this point, I think I'd probably like to hear some of those questions. So anything, or maybe I can even start with a little check to see what we remember. So if I were to ask you what the power rule is, what is that? This is where you guys come in. Just let me know what the power rule is.
Is it n times x to the n minus 1?
Almost. So this is very important. And I know at this point, students never agree with me, or a lot of the times, I shouldn't say never. A lot of the times, students don't agree with me that they need to remember the whole thing. But when it comes to a rule, it's actually very important that you remember the whole thing, both the left and right side of the rule. So what you just told me is the right side of the power rule, which is correct. But it's very important that you also remember the left side.
So f
Um,
prime equals
so
f prime of x equals that, or
Well, if you want to say f prime, you'd have to first define f. So the power rule, I'd say something like it's d dx of x to the n. So that basically says if I want to take the derivative of something that looks like x to the n, then it would give me nx to the n minus 1. So that's one way to write the power rule. Or if you want to use f prime, it'll take 2 lines to write it down. So you would say something like if f of x equals x to the n, then f prime of x equals nx to the n minus 1. Okay. So the rule is the entire thing. So it's both the left and right side of the equation. That's the more concise way to remember the rule. If you want to use f of x, you'd have to kind of remember a whole sentence. So I'd probably like to remember it the top way. But the left side is actually important because there are a lot of situations in which I find students get in trouble because they're trying to apply a rule in a situation where it doesn't belong. And and a lot of the times it's just because they don't know the left side of the rule very well. They don't realize that this rule doesn't apply to this thing that I'm trying to apply it to. So yeah, that is the power rule. What if I were to ask you, what is the product rule? Product rule.
Is it derivative of f of g?
F of g.
Fg.
Okay, so of f times g.
Yeah,
Okay,
equal to
so this here is a multiplication. Yeah, equals.
f prime g plus fg prime.
Right, that's the product rule. So that tells you how to actually differentiate a product of two functions. What about the quotient rule?
Can you go up a little bit? Or just look at that?
Quotient rule?
It's d dx of f over g equals f prime g minus f of g prime all over g squared.
Right, that's the quotient rule. What if I were to ask you, what is the chain rule?
Is derivative of
Mhm.
f of x to the f of g. I mean g of x.
F of g of x.
Yeah, equal to f prime of g of x times g prime of x.
Right, so that's the chain rule. What if I were to ask you, what is the derivative of e to the x? Derivative of e to the x?
It's just e to the x.
It's just e to the x. What if I were to ask you, what is the derivative of ln of x?
Just
1
1
over
over
x.
x.
1 over x. What if I were to ask you, what is the derivative of a to the x, where your a greater than 0 is a constant?
Is it x to the x times a to the x minus 1?
No.
I think
Why?
it's just zero.
What happened here? What is the issue? Why is that no? What did they try to do just now?
Because the exponent is a variable and it's not a number. Like you flipped it. Before it was
Right.
that it was x to the like some number. Now it's like some number to the x.
Right. So this is a common error. And this goes back to what I was mentioning earlier, why it's important for you to remember the left side of a rule. So because someone knows the power rule as they only remember the right side, like, okay, if I see a power, I bring it down and then subtract 1. That puts you in a situation where every time you see something to a power, you think that's what you're supposed to do, but that is not true. If you go back to the power rule, you want to be aware that this is a common error. It's an incorrect application of the power rule. And here's why memorizing the left side is very important. So when you look at the power rule, you have to realize, what does that apply to? You have to realize that, for one, this guy and the base are the same. Whereas here, that and the base are not the same, right? So you're automatically not in the situation there, right? Also, you should recognize that your x is the variable and your n is a constant. In other words, the power rule only applies when the variable is the base and the power is a number, it's a constant, right? And the variable base is exactly the same as the variable you're taking the derivative with respect to. That is the power rule, right? In this case, the base is a constant and the power is a variable. Here, the base is the constant and the power is the variable, right? So that's the danger of memorizing one part of a rule. If you just think, oh, the power rule means if I see a power, I move it down and subtract 1, you're going to end up in a lot of trouble in a lot of situations. No, the power rule is very specific, and the left side of the rule tells you in what situation this applies. So here, it's a whole other rule. And I'm going to do some examples so you can actually see the difference in applications here. So what is the actual rule? Does anyone remember?
Is it ln of a times a to the x?
That's correct. I prefer to write it as a to the x ln of a though, but that's correct. Because the thing is, when you write ln of a times a to the x, sometimes people might think the a to the x is inside the ln. I do want to emphasize that it's not inside the ln. So I would tend to write the a to the x first, but that is the rule. So at this point, let's actually do an example. So example, when you see something like the derivative of x cubed, that is 3x squared, and that's because of the power rule. This guy here is called the general exponential rule, by the way. If you instead see something like this, the 3 is the base and the x is the power, then it is not the power rule. This is a general exponential rule. The derivative of that is going to be 3 to the x ln of 3. Right? It's very important that when you memorize the rules, you remember both sides of the equation. You remember it's the entire rule, because the left side is important because it tells you when that rule applies. Okay, and if you're not careful, you're going to end up in situations that they look almost the same. I mean, an x cubed and a 3 to the x, they look like they're almost the same thing. Well, they're actually not. If you know the graphs of these guys, you'll know that they're actually very different. But you see what I'm saying? In terms of the mechanics of actually writing them down, of how they fit on a page visually, they're very similar, right? You have a big base and a small thing to the top right corner, right? And just by them having that similarity when writing them down, your brain is very natural to get into certain habits. It gets into the habit of every time it sees a power, it moves it down and then subtracts 1 from the power. So you just think that every time you see something like that, that's what you're supposed to do, but it's not, right? And that's why remembering the rules, both sides of the rules, I definitely recommend that, so you don't end up in situations like this. So the power rule only applies when the base is the variable and the power is a constant. So when the base is the independent variable specifically, and power is constant. Now, if you're in a situation where the base is a variable, but it is not the independent variable, so what if I had something like this? 2x cubed plus 1 to the 5th. How would you do that one?
So it would be 5 parentheses 2x cubed plus 1 raised to the 4th power, and then times 6x squared.
That's correct. What rule did you apply here?
The chain rule.
So you applied the chain rule, right? So here was a situation where the base was a variable and the power was a constant, but you don't just directly apply the power rule, because the base is a variable that is not the independent variable. It's a amalgamation of the independent variable with some other stuff. So this counts as an inside function and an outside function. So you'd apply the chain rule. So these are 3 very similar situations in terms of the positions of where things are, but they require 3 very different rules. And it comes down to you knowing what the rules are to know when you should apply which rule, at what time, in what way. So in the last situation, I did end up applying the power rule at some point. I did apply to differentiate the outer function. So here, this is like, it's like an f of g of x, where my f of x is the x to the 5th, it's the 5th power, and my g of x was the inside function, 2x cubed plus 1. And I talk about inner and outer functions in class as well. So you can be in very familiar situations, but they are all handled very differently. And how would you know when you're supposed to do which? Well, by knowing the rules very well is how you're going to know. And by knowing the rules, I mean knowing both sides of the rule, the left side and the right side. Students have a habit of only memorizing the right side. You'll get in trouble doing that. So yeah, so that was very important there. That was something I was going to emphasize later on anyway, but it just naturally came up because it's actually a very common error. So be careful of that. Yeah. And also for the quiz, there will be problems where I literally just ask you to do things like that. Tell me what the rule is. Just complete the rule, complete the formula, right? So I will ask you questions like this. So you will get points just for knowing what the formulas are. But then of course, I'll also have examples where you have to actually use it and you have to apply it and you have to recognize which rule or formula should I be applying at this point, right? So you should know the difference between these three types of examples, right? So on one hand, they're all very familiar because they're all about something to a power. But on the other hand, as far as differentiation goes, you would deal with these three situations very differently. And you would know that because you've memorized the rules. Okay. Is there any other rule that I told you about? Here's another example. Let me know how you would do this one. So with 4. How would you do that one?
You would use the division rule, or quotient rule rather.
Okay, and what would you get?
So it would be, you do x squared times the derivative of the numerator, which would be 2 plus 6x minus 12x squared. And then you
Okay,
do minus the numerator, so minus 2x plus 3x squared minus 4x cubed, times the derivative of the denominator, which is 2x, all over the denominator squared, which would be x squared to the second power, so x to the fourth.
right. So here, what you did was you applied the quotient rule. And so what you did was here you took the g and then you multiplied by the f prime g, it's the same thing. Then minus, you left the f and you multiplied by the g prime. And then down here you put the g squared. So that's this part, that's this part, that's this part, that's this part, and that's that part. Okay. Now, of course, if this is like a multiple choice problem, I wouldn't give you the answer that way. I'll actually simplify that answer and tell you what it is. So how would you go about simplifying this?
I guess what I would do is I would distribute the x squared on the left side of it and 2x on the right side, and then
Yeah.
try to
I
like
mean, you
cross
could
that with.
reduce before that, but I guess you can do that as well. You could actually, there's a common x, right? So you could actually reduce that first and then expand.
Oh, okay.
So you would have 2x plus 6x squared minus 12x cubed minus 4x minus 6x squared plus 8x cubed all over x cubed. What would you do now?
Now I would look and try to see like where I could simplify. So the 2x and the negative 4x would become negative 2x.
Mm-hmm.
The
That takes care of this and that.
6x squared and the negative 6x squared cancel with each other, so they go away.
Mm-hmm.
And then the negative 12x cubed and the 8x cubed becomes minus 4x cubed.
Okay. Can you simplify further?
Yes, from the numerator you could pull out a negative 2x. And that would leave you, 1 plus.
1 plus 2x squared
Mhm.
all over x cubed. And then?
You could cancel the x in the numerator and make the denominator x squared.
Okay, so you end up with minus 2 times 1 plus 2x squared over x squared. In fact, you can even think of this as, say, something like minus 2, 1 over x plus 2, or something like that. 1 over x squared plus 2, etc. So either this or that. Okay, now, there's a better way. So what you did was correct. There was actually a better way to get to the answer. Does anyone actually see a better way to get to the answer?
Can you just wait, actually, I don't know if that would work. You could separate it into like a bunch of additions, maybe.
Okay, and what would that look like? So here you're not differentiating it, you're just taking the x squared and dividing it into each part, right? So the first part would look like what? 2x to the minus 1. The second part would look like a 3. The third part would look like a 4x, yeah?
Yeah.
And now what?
You could just use the normal power rule on each one of them.
The derivative of 3 is 0, and you get that, right? Very nice version of the answer. You will recognize that this is the same thing because this is minus 2 over x squared minus, is that a minus 4? So this is the same as minus 2x to the minus 2 minus 4, which you'd realize is the same as the answer here. Now, I want you to compare what happened here, right? Jumping into the quotient rule, doing all this calculation, all this simplification to get to this answer, which chances are, if it's a multiple choice problem, that's how I'm going to type the answer, because why am I going to type all of this when I could just type this, right? Now compare that to here, where we got to the answer a lot quicker, right? With a lot less work. So there's something else I wanted to emphasize. So a big part of these recitation sessions, which is why it's very important that we have them, is that I want to emphasize the things that students wouldn't necessarily pick up on. So yes, you guys will remember all the rules, and that's good. You're supposed to do that. However, there are some nuances into how you would apply things. Just because you can apply a rule doesn't mean that you should all the time. Not that you'll get something wrong, but you can end up in a situation where you're working a lot harder than you have to. So there was a segment in class where I kind of mentioned, just because you know that the quotient rule can apply doesn't mean you should just jump into the quotient rule without thinking about it, right? Yes, it'll work. Yes, you'll get to the answer, but also you might be working harder than you have to, which, sure, if you're great at algebra, you'll get through it. However, it'll take you more time. And honestly, the more time you spend working out a problem, the more chances there are for you to make a mistake, right? So it's not very efficient to actually just because a rule can apply, you just apply it. So I do recommend that whenever it's a matter of you want to do something like the quotient rule or the chain rule or anything like that, check quickly to see if simplifying would work first, right? So in this situation here, you could easily simplify that before jumping into the quotient rule. Just because you see a division doesn't mean just jump into the quotient rule, right? You can simplify things first. Then you can apply the quotient rule if you have to after that. But oftentimes, if you can simplify, you won't even need a sophisticated rule as you would have needed first. Another common type of problem where I see students mess up in this situation would be if I ask something like the derivative of ln of the square root of x e to the x over 2x plus 1 to the 5th, right? Now, there's a rule that covers this case that tells you how to find ddx, pay attention to the variables here, of ln of something, right? Where that something is u. It could be x, it could be another function. What was that rule? The derivative with respect to x of ln u?
Is that the power rule?
What do you mean the power rule?
Oh, do you want the answer? Oh,
Yeah, the answer. If I take ddx of ln u, just tell me the general formula.
so it's 1 over x, 1 over u.
No.
Isn't it u prime over u?
U prime over u, because you need to apply the chain rule, right? So it's u prime over u. Now, a lot of students will know that answer. And so they'll see a problem like what I just wrote down to the left here, ln of the square root of blah, blah, blah. And they'll try to apply that blue rule. Now, the blue rule is correct. And so what you'll see is students often try to apply Now, what would it happen if you tried to apply that rule directly to this problem? You're going to end up in a situation like this, where you're going to take 1 over the thing, and you're going to have to multiply by the derivative of the thing. So here you have that this part here is your u, and this part here is your u prime. Now, of course, as you can probably guess, students often mess up with the u prime here. What is involved in actually doing the u prime here? Well, you really have x e to the x over this thing all to the half power. So there's an inner function and outer function. So you'd have to do the chain rule. So you're going to do the power rule for the outside. And then when you get to the inside, what are you going to do? Quotient rule. So you have to end up doing a chain rule with a quotient rule for the inside function. And it gets messy very quickly. Gets messy very quickly. And even when the students know what they're doing, mistakes are common here. That being said, there is a better way. So there was a better way to approach this. Anyone can tell me a better way? So let's say you didn't directly want to apply the ln rule. Oh, by the way, I do want to make a comment up here since it actually came up a little bit earlier. We do have a rule that ddx of ln x is 1 over x. I do want you to pay attention though, that here we have a u, here we have an x, versus here we have an x, here we have an x, which is why the answer to the first one wasn't 1 over x or just 1 over u, because it's actually a different situation. Your u here is an inside function. So you actually have to apply the chain rule, right? So that was the difference. And again, this is why knowing the left side of a rule is very important. You only get 1 over x if the thing inside the ln is exactly equal to the thing in the denominator of the d dx expression. Okay. All right, a better way to do this?
Can you like say that ln, like the inside part of the ln is raised to the 1/2 power, and then move the 1/2 in front of the ln?
Right, so this is ln of this to the 1/2. Move the 1/2 in front of the ln. Again, we're not differentiating yet, so we have to keep the d dx. Then
you wouldn't use the product rule because the 1/2 is just like a constant. So you could just do, I guess the 1 over x rule, but you'd have to like flip the denominator because you're putting it.
yeah, you're actually good running back into the same issue here. You're still trying to apply this rule at a stage where it's just more complicated than it has to be.
I don't know then.
Like you brought the 1/2 power down. Obviously that makes your life a little bit easier, right?
Yeah.
Anything else you can think of that would make your life easier? Where you don't have to, for example, take the derivative of a division?
Can you find a way to cancel the ln and e? Like make them cancel? I don't know what else.
When do an ln and an e cancel? Ln's and e's cancel when they're right beside each other, right?
Yeah.
Do you have that situation here?
No.
No. Any other rules you can think involving ln's or logs or?
I am at a loss. I don't know.
You have a log of a division. Does that conjure anything up?
Log of division.
Log of division? Anybody?
I think you can just use the rules that we learned from
Way
logs.
back, right? Like lecture 2 or something?
Yeah.
What rule are you thinking of?
Sorry, it's the one where you can subtract.
There's
No,
a rule that
yes.
says when you have the log of a division, you can actually subtract the logarithms. Remember way back when? Yeah, that was like in the very beginning of the class, right? So here I do have a log of a division. I can actually just subtract these. So this is ln of the top minus ln of the bottom. Now notice.
And then you can expand that ln x
Yeah,
to the e, so
how?
it's ln of x plus ln of e to the x.
Right, there's another rule that
cancel.
says when things are multiplying, we can think of that as an addition of logs. So that's what happened here. Apply here. And then you're going to apply here. So you can actually even break this down even further. The first one is ln of x plus ln of e to the x minus this one here. I can just actually move that power down. Okay. Now look at what we have here. We know that derivatives distribute across sums. So the derivative of this sum is just the sum of the derivatives. I only have to find the derivative of this, the derivative of that, the derivative of that. And in fact, this one can simplify even more because of the ln of e to the x rule that we mentioned up here. Right? So that's actually just an x. Now compare this to the original. Would you rather having to find the derivative of this or the derivative of each of these, right? Which one do you think is going to be less time, less work, less complicated, right? Now, individually, you can find the derivative of these guys pretty easily. I'm still in blue. What is the derivative of ln x?
1 over x.
Derivative of x?
1.
What's the derivative of this one? 5 times ln of blah, blah, blah.
5 over 2x plus 1.
No. What rule applies here?
Is it the u prime over u?
Right, it's the u prime over u, right? So this is d dx of ln of u equals u prime over u. How do I know that rule applies? Because I have 2x plus 1 and not x, right? The rule where I just put 1 over the thing applies because I know the left side of this. The thing where I just put 1 over the blah only works if there's an x inside the ln. It does not work if I have something other than an x inside the ln. If I have something other than an x inside the ln, this is the rule that applies. Okay, which means I have to multiply by the derivative of that thing. So I need to multiply this by 2 because of the chain rule. So this is going to be 1/2 times 1 over x plus 1 minus 10 over 2x plus 1. Now, one thing I want you to notice here is that up to this stage, up to this point, we're only applying algebra rules. I want you to appreciate that I wasn't doing any derivatives, right? My d dx was here the whole time, right? I didn't actually start to do any derivatives, right? I was only applying algebra rules. What do I know about logarithms? How to simplify a logarithm. So I simplified first, and then I end up in a situation on this step here where now I can apply the calculus in a lot easier ways, right? This also goes back to something that I mentioned a long time ago, where I basically said, if you fail calculus, it's because of the algebra. It's not because of the calculus, right? So the hard part of this class is actually algebra class. It's about knowing how to simplify stuff, knowing how to break things down. Normally when you're applying the calculus, it should come at a stage where it's kind of easy to do it. It's a one-liner kind of thing. The calculus is actually a very small part of the problem in general. And this will be true when you're going on further into further topics where we're doing more application stuff. So yeah, you need to really check your algebra. So all those rules that I mentioned way back in lecture 1, lecture 2, all those basic algebra rules, how to simplify fractions, how to factor stuff, how to cancel stuff, how to solve equations, how to simplify a logarithm. These are things that are very important for you to remember. So don't just memorize all your calculus rules, because that in and of itself isn't going to help you as much. That is important. Memorizing the calculus rules is important. And as you guys have seen here today, memorizing the entire calculus rule is very important, including where we were. Memorizing the left side of the calculus rule is also very important, because you can end up in two situations that look very familiar. However, they're not supposed to be treated the same way. How you're going to pick up on this is from the left side of the rule. Notice in the top one, for example, I have d dx, and then I have ln of something that is not an x. That requires a chain rule application. If I have ddx and then I have ln of specifically x, that is 1 over x. So if you memorize a rule with x's in it, you have to understand if anything other than just x replaces the x, that thing requires a chain rule application. You need to follow the rule pretending it was just an x, and then you have to multiply by the derivative of that thing, okay? So these are just some subtle points that students often overlook. So this is why I wanted to have this session, make sure that we're all on the same page. So some very important tips here. Muy importante. Memorize rules exactly, including both sides of the equations. If you only memorize the one side of a rule, you are doing yourself a disservice. You're going to end up in a situation where you're not going to be applying a rule correctly because it's not going to apply to the thing you're trying to apply it to in the way that you're trying to apply it, because you just never really paid attention to when that rule should be applied. You can get through this by memorizing the entire rule, right? So a lot of times when I would ask a student, what's the power rule? They always just say nx to the n minus 1. That's not the power rule. Do not think of that as the power rule. Remembering it that way will get you in trouble. The power rule is the derivative with respect to x of x to the n is nx to the n minus 1. The power rule is the entire equation. Make sure you memorize the entire equation, because otherwise you're going to end up in situations where you're not applying a rule effectively. So that's an important tip. Second tip. My pen was messing up just now. The second important tip. Try to algebraically simplify expressions before applying calculus. You won't always be able to do this. There are some times where I give you something that's semi-complicated and you just have to deal with it. You just have to kind of suck it up and just go through the calculus rules. But there are some times where the thing I gave you, you could simplify it first and then apply the calculus rules to easier looking things. You don't always have to do this, but when you can, you should. You won't always. So maybe some examples there. Example, if you see ddx of like what we had before, 3x to the minus 2 plus 4x to the 7 over x to the 5th, simplify first. If you see something like 2x plus 3 over x squared plus 1 cubed, quotient rule, right? Because you can't simplify this, right? You're not going to be able to like divide the x squared plus 1 cubed into each individual term without having something where you have to end up using the quotient rule anyway. Like if I take the 2x over the x squared plus 1 cubed, like I would have to do the quotient rule or bring it up and do the product rule anyway, so might as well I just started with the product rule. So here you can easily simplify in the first example. The second example, you can't really easily simplify that. So you, someone got kicked out and coming back in. So you would just jump into the quotient rule versus something like d dx ln of the square root of x squared plus 5 over xe to the x. Simplify first. Right? Use your log rules to your advantage. You can take that radical, turn into a half power, bring it in front. You can turn the division into a subtraction of logs. You can turn the multiplications into an addition of logs, right? So you do that first. However, if you had something like this, no, just apply the rule. Which rule? d dx of ln of u, right? Because what's in here is not just x. So you don't think of the d dx of ln x rule, which just tells you it's 1 over x. It's something that's not x, which is a whole other rule in your mind, or it should be, and you would have this. By the way, the d dx of ln x rule is included in this rule, because if your u equals x, then your derivative is just 1 anyway. So you'll actually get back that old rule. So whenever you are memorizing rules, I already recommended this in class. So better to memorize the chain rule versions of rules if you have to choose. So some students don't mind memorizing. They're very good at it. They can memorize 100 rules, right? You know, they're biologists, so they're used to memorizing all sorts of stuff or whatever. So if you're good at memorizing, memorize everything. Memorize all you want. If you're the kind of person who you're not really into memorizing and you're like, man, I want to memorize the minimum amount of things that I have to memorize, then if you want to forget some formulas, I would forget the non-chain rule version. It's better to memorize the chain rule version. So, so if you have a rule that says d dx of ln x is 1 over x, you have a chain rule version of that rule that says if you have something that's not just x, you have to multiply by a derivative. You have a rule that says e to the x is equal to e to the x. There's a chain rule version of this rule. The derivative of e to the u is u prime e to the u. Take the derivative of the power, multiply by the original function. You have a rule that says d dx of a to the x is a to the x ln of a. The chain rule version of that is if you have a to something that's not just an x, it's u prime a to the u ln of a. It's better to memorize these. In fact, these guys include the guys in the left column. Right? Because if your u is equal to x, then your u prime is just 1, and you realize that the rules just devolve back into the previous rules here. So yeah, that's another tip. Another common error that I should point out. Ln of a plus b is not ln of a plus ln of b. You cannot distribute a log across a sum. You can, but we didn't learn how to do it. It will actually take an infinite number of terms to do this. So just assume for the sake of argument that you cannot. In a class like Math 1207, which is for Calc 2 students on a whole other track than what you guys are on, you would learn a technique in that class where you could actually do this. You can expand a radical, you can expand the sum of logarithms, but even then when you can do it, it's not easy. It's actually pretty hard to do, right? So for example, in this example that I was mentioning, to differentiate ln of x squared plus 5, a lot of students would make the mistake of distributing the ln and think of it as ln of x squared plus ln of 5 and then differentiating that. That would be incorrect, okay? So I just want you to be aware of that. And by the way, everything I'm talking about here, I did go through them in the lectures. So if you didn't actually watch the lectures, then chances are this is going too fast for you and you probably don't have any idea of what I'm talking about. If you did watch the lectures, but you didn't really pay attention, this is meant to actually tell you about some things that you should be paying attention to that chances are you didn't. A lot of the students pay attention to some things, but they don't pay attention to other things. And these things might cause you guys to make errors. So I just wanted to make sure that those are pointed out. That's the purpose of this session. So that's just some things on the basic rules. Those are some of the biggest issues I tend to find. But yeah. When it comes to second derivative, going back to the topic list here, second derivative just means take the derivative of the derivative. And you have notation for this. You can be f double prime or d squared y over dx squared, etc. So second derivative just means take the derivative of the derivative. Same thing, third derivative means take the derivative of the derivative of the derivative, etc. What you do need to know about second derivatives, though, is what their interpretation is. The second derivative can tell you about concavity and inflections. And the first derivative test and the concavity test can help you identify these locations. So you should actually know that. So maybe I'll talk about that for a little bit, or maybe just have you guys summarize to me, make sure that you do understand this. So second derivative equals derivative of derivative, right? So the notation, if you're using the prime notation, you can write that as f double prime or d squared y dx squared. If y equals f of x. Tell me about concavity. There are two kinds of concavity. What are they?
Up like a cup and down like a crown.
I love that you have that whole mnemonic memorized. That's awesome. Yeah, it's concave up and concave down. But yes, means up like a cup and down like a frown. Okay, there are two types. Okay, like if you're talking to anyone other than me, say the up like a cup part in your mind, because they're gonna be wondering like, what are you talking
Yeah,
about?
I like never
But
heard
yeah.
it, but I liked it.
Yeah, it's a way to remember it. Okay, so there are two types, right? There's concave up and there's concave down. So yes, with that, I want you to remember the mnemonic as a thing, concave up like a cup, right? So that tells you what the shape of the graph is. So that means the shape is like this, right? Or like this, or like this, right? So these are the kinds of shapes, right? In a region where a function is concave up, that's how it's going to shape. There's going to be a bulge that is kind of like a smiley face or kind of like a cup holding water, concave up like a cup. Concave down, this means concave down like a frown. So this tells you about when the graph is shaped like a frown, right? It could be shaped like a frown and decreasing. It could be shaped like a frown and increasing as well, right? So it can be any of these shapes. Now, by the definition, f is concave down on an interval I, well, in this section is concave up. Tell me about a computational way that you can check this. Concave up, how do you know where something is concave up?
It's concave up if f double prime of x is greater than 0.
Right, so concave up is when it's the second derivative is positive, it's up, it's positive, it's feeling happy, it's concave up like a cup. Okay, and for here, this means that your f double prime is negative on I. Right? So you can tell where something is concave up versus concave down by checking the second derivative. Find the second derivative. All points where that guy is positive, it's the shape of the graph will be concave up. All points where it's negative, the shape of the graph will be concave down. Okay. What about inflections? What is an inflection? What happens at an inflection?
It's where the concavity changes.
It's the point where concavity changes. Right? So this, if you're looking at shapes, it could be something like this, right? Where we were concave down on this side, then we move to concave up. Or it could be like this, right? So here we were concave up, then we switched at this point to concave down, or anything like that. So it's like when you have this little flip in how the graph is behaving, whether it went from a frowny face to a smiley face or a smiley face to a frowny face, we call that an inflection point. It can do this either way, so it can be decreasing while it's doing it as well. So these guys are inflection points. So this. Okay, so you pretty much, to find an inflection point, find where the second derivative is 0 undefined, and then check if it changes sign on either side by plugging in x values a little bit to the right and a little bit to the left. If you realize that the sign changes, then the point you're looking at is an inflection point as long as your graph is defined there. So that would be the concavity test. So the first derivative test helps us check for maximums and minimums, where we're increasing and decreasing. These are some things that are also important. So remember that increasing means the first derivative is positive. Decreasing means the first derivative is negative. And if you're, depends on how you're looking at it. If you're increasing on the left side and decreasing on the right side, you will hit a maximum in the middle if your graph is defined exactly in the middle. And if you're decreasing on the left side and increasing on the right side, and your graph is defined in the middle, then you would have a minimum in the middle. So things of that sort. So there was a lecture, I forgot exactly what number I did this, but where I wrote out this whole table where I can tell you, okay, this is what, based on what the derivative is, this is what you can interpret from the graph. So that table is actually very important to know. If you don't know that table, that will be an issue on the quiz for sure. Yeah, so I want to say it's either lecture 9 or 10 where I did that table. Yeah. Okay. So those are just some concepts that you should know about. So I can ask you questions like that. Here's a function. Tell me where it's concave up. Here's a function. Tell me where it's concave down. Here's a function. Does it have a maximum? Does it have a minimum? Find these, right? So things like that I can ask you about. And as well as I can give you a graph, I can give you a picture and then ask you, identify the intervals where we're concave up, identify where we're concave down, things of that sort. Identify, where does the derivative, existence of the derivative is another thing that was covered. Did I have that in the? Let me throw that in. Existence of the derivative. So the derivative is a very powerful entity. However, it does not always exist. There are times when you cannot find a derivative. These are things that you should need to know. Existence of the derivative. F prime does not exist at points where, what are the things? Tell me one situation where a derivative won't exist.
A corner or a cusp.
Right. At sharp corners. Right, so if I give you a picture and there's a sharp corner or a spike in that picture, you can tell me, you know what, at this point, at this x value, there is no derivative, right? So if I have, a spike like that, very sharp corner. So for this x, f prime of x does not exist, right? At sharp corners, can't find a derivative. Tell me another situation where a derivative does not exist.
If f of x isn't continuous.
Right. Where f of x, the original function is not continuous. Right? So that's like where there's a gap or something, right? So you have a graph, there's a hole in it, or you have a graph where it shoots up to infinity and down like that. So if this here is your x value and this here is your x value, f prime does not exist at these points. Third situation.
Vertical tangents.
Right, where you have a vertical tangent, where f has vertical tangent. Because the slope of a vertical line is undefined, and that's literally what the derivative is. It's a function that tells you about the slope of the tangent line. So this is very strange. Probably not going to test you on this, but just in case I find a way to test you on it, because it's very hard to show this on a picture. So, however, there are times when a function has a very weird behavior, like for a split second, it goes vertical. So this can happen at certain types of inflection points. However, if you can surmise that a tangent line is vertical, it has no slope. So f prime undefined. Yeah. Let's see. Yeah. So just know about that. When it comes to existence of derivatives, I would test you on that by like just giving you a picture, right? And so kind of like on the last graph where I gave you a picture and asked you, where is it continuous? And you can tell me, oh, it's not continuous for this x value, right? Where I gave you a picture. So for the quiz, I can give you a picture and I can ask you, where is the derivative undefined, right? Where is f continuous? Where is the derivative exist? Where does the derivative exist? Things of that sort. So you should be able to tell on a picture when a derivative doesn't exist. And that's pretty much the only way I quiz you about this, right? So derivatives are important, but it's also important for you to know when you're not allowed to actually use a derivative. Let's, okay, what else? Implicit differentiation. At this point, I would only test you with the very basic stuff, implicit. For quiz. In the bonus, I might test you with more sophisticated situations, but for quiz, I believe I get into a little bit more nuances and complexities in lecture 15. But for the quiz, I just want you to know the basic. For quiz, just know how to find, say, dy dx if given like your x's and y's are mixed together on one side, right? So implicit differentiation comes into play when you don't have your dependent variable isolated. So you can't write y as a function of x where there are only x's and y's described completely in terms of x's. You have your x's and y's kind of mixed together in their own functions. They're all entangled together, and you still want to find the derivative there. So example, find dy dx if, let's say I know 2x squared y cubed minus 7y to the 6 plus ln of x equals 4x. Okay, so here your x's and y's are mixed up. You don't have neatly y on one side equals some function of x. However, we might still want to be able to find the derivative. Yeah, maybe someone can tell me how to do a problem like this. Or maybe at this point, you can actually describe to me the rule. Tell me about the process, how you would go about actually doing this. Anyone describe to me like how you would approach it?
I think you need to start by getting the y's on one side and the x's on the other.
No, not in general. I mean, if possible, yeah, but most of the time that won't be possible. Here, technically, that is possible if I think of it as a quadratic, but the function is going to be so complicated, it's just not going to be worth it. Like I can think of y cubed as the base variable and think of this as a quadratic and then use the quadratic formula to solve for y, not worth it. However, it is worth pointing out that it's not always possible. For example, if I put a 7 here, now it's impossible to isolate y. What do we do? So sure, you can isolate y if it's possible, but as I showed in class, it's not always possible, and sometimes it's just not efficient. Like your y, if you isolate it, it would just be such a complicated function. It's just not worth your time.
So for the first term, you would have to use the product rule.
Okay. But what is the idea here? So you differentiate as usual, except.
So when you have y, like y to the third, for instance, let's just,
Yeah.
if it was by itself, it would become 3y squared dy dx.
Right, except when differentiating a y term, you need to multiply by y prime. because you're applying the chain rule. Your y is an inside function. So when you see y cubed, don't just think of it as a y cubed. There's a whole like function cubed. And so the chain rule that we looked at earlier applies. So once you differentiate the y, like differentiate the outer function, like you go from y cubed to 3y squared, you have to remember that that y is actually an inside function. So you have to multiply by the derivative of the inside, you have to multiply by y prime. So you apply the chain rule. But mechanically what it means is just when you differentiate the y term, multiply by y prime, right? Now, this can get a little bit more complicated depending on who your independent versus dependent variables are, but I get more into that, I believe, in lecture 15. So you don't really need to know that for this quiz. I'll probably put it on the next quiz or something like that, or in a bonus problem. But very basic, if I only have the two variables x and y, x is my independent variable, y is my dependent variable. I know this because the independent variable is the one on the denominator. So I know I'm thinking of x as a dependent variable, meaning anyone who is not x, I need the chain rule for that person. And y is not x, so I need the chain rule whenever I'm differentiating the y. But that's basically the rule, right? So to look at this guy, right, so now that we have this idea, how do I go about applying it here? So I just go through and differentiate each term. Let me put it that way, differentiate each term. Just as usual, meaning you have to obey all your derivative rules, it still applies, yeah, go. So the first term, hello, are we still out there?
So for the first term, you would do, I guess it would be easier if you put the 2 on the outside, like in order to do the multiplication. So like you would do 2 parentheses.
Not really, I don't think so.
All right.
You can just think of this as two functions, like there's a 2x squared, and then there's a y cubed.
So then I guess you could do,
so product of, so you need the product rule. This guy here is a function to 7th power, need chain rule. For this one, you need the d dx of ln x rule. For this one, you need power rule. So you just go through and you know that you're just going to kind of do things how you normally do it. The only difference is now when you're doing a y, when you're differentiating a y term, you have to multiply by y prime. So in the first situation, to do the product rule, I differentiate the first function, leave the second one alone. So that's 4x times y cubed. Plus, now I leave the first function, differentiate the second one. So that's going to be 3y squared, and then I multiply by y prime. So according to this rule, when differentiating a y term, you need to multiply by y prime. That's what I mean. You literally just multiply by y prime whenever you're applying a derivative rule to a y function, right? So this is the product rule on the first part. So here, think of this as f and g. So this here is f prime times g plus f times g prime. Product rule on the first part. Okay, and you go through and you just do everything as normal. So in the second one, minus 49y to the 6, I need to multiply by a y prime. To differentiate ln x, that's just 1 over x. To differentiate 4x, that's just 4. So I just go through and I differentiate each term. The only difference is whenever I apply the derivative rule to a y, I multiply by a y prime. Now what you do is you solve for the y prime, right? Because that is your dy dx. Right? So if I look at this guy right here, so if I look at this guy right here, y prime is in this location and that location. We want this. Now it's just a matter of solving for that like algebra, right? So again, algebra is coming up. So you leave all the terms with the thing you want on one side. And then you bring everything else to the other side. Then you'd factor out the common term. So that would be 6x squared y squared minus 49y to the 6. And then you just solve for that by division. And that's your answer. So, and we're actually way over time here. So let's wrap up there. But we went through all this in class. So hopefully this jogged your memory. Hopefully I shown a light on things you should pay attention to that will help you not get in trouble when certain nuances come about. And you have a basic understanding of how to go about doing these things. Of course, you just watched those lectures today, so maybe even at this point you don't fully understand how to apply things. So maybe go through some of the homework problems, go through some of the textbook problems. Make sure you memorize the rules, memorize the entire rules exactly. And if you have any questions, I suppose you can shoot me an email or something before next week. So next week we have a quiz, and yeah, then we have class after. So unless there are any quick parting questions, we'll end there. Any questions? Okay, so we're going to wrap up there. Thank you for your attention. Thank you for participating, and I'll let you guys go.
Thank you.
Thank you.
Thank you.
All right, take care. Have a good week, guys. Good luck for next week, and I'll see you in the next one.